everyone. I am Dr. Jagadha Saravanan, Associate Professor in the Department of Mathematics, Institute of Aeronautical Engineering, Hyderabad. The topic for discussion is problems on Poisson distribution. This lecture includes definition of Poisson distribution, mean of Poisson distribution, variance of Poisson distribution, and we are going to solve the problems using Poisson distribution formula. Here we are noticing here 0 to 6. Here 0 to 6, it is up to infinity it goes on. Now the definition of Poisson distribution. This is derived by Denis Poisson, the French mathematician. He has given this definition, that is using the binomial distribution formula, the extension he did and derived a new formula, and finally his name only named for that formula has become Poisson distribution formula. That is a random variable, the capital X. We know it very well, the random variable, the functioning, what it does, that is any sample space. The sample space, it's nothing but it has the sample points. The sample points, now if your coin is there, only one coin we have. So we know it, if we toss that particular coin, we will be getting the output, head or tail. So these outcomes are called as sample points. These sample points are converted into real numbers. That is the work this random variable, the capital X, it does. That's what it is called as real valued function. Okay, fine. Is said to follow a Poisson distribution if it assumes only non-negative values and its probability density function is given by, if you are noticing here, the probability of x equal to x, it's nothing but p of x. So the Poisson distribution, the formula is e power minus lambda power x by x factorial. Here x is taking the value from 0 onwards, but it is not finite. That's what it is written here, dot dot, it goes on. It takes larger value or infinity. Otherwise, the function is 0. Where, if you're noticing this, the parameter, the lambda is positive. Now, mean and variance of the Poisson distribution. The mean, here noticing the mean of the Poisson distribution, the mean value is mu. So the mean of the Poisson distribution is lambda. Sigma square, which is this is the notation for variance. That is, variance of the Poisson distribution is lambda. Now, so lambda is playing the role for both mean and variance of Poisson distribution. So this is the Poisson distribution formula. Once again, it is kept here. E power minus lambda into lambda power x by x factorial, and this lambda is a positive number. Now problems we will concentrate. If a bank received on the average 6 bad checks per day. So per day they are receiving 6 checks. They are in bad condition. Average. It is not given a total number. Average is different. The average meaning is Monday. I'm purchasing some 4 flowers. Tuesday, 5 flowers. Wednesday, 6 flowers. Average. So 4 plus 5 plus 6. So 15 by 3 average we can expect. I'm purchasing 5 flowers. So this 4 count is different. Monday we purchased 4. So here also we didn't receive daily 6 average. 6 checks they are in bad condition. Find the probability that it will receive 4 bad checks on any given day. So they are asking us the probability of this specific target, that is x equal to 4. So now the probability, the distribution formula is e power minus lambda into lambda power x by x factorial. Solution. The Poisson distribution formula is, this is the formula. Lambda equal to 6. Lambda, it's nothing but mean of the Poisson distribution. Mean. Here it is. The word it is not given directly mean, but average it's nothing but mean. So that's what a lambda equal to 6 has taken here. Now, so specific target. So we know it now. This is the formula. So the lambda value we picked from the question. X is a specific target. The specific target is 4. So we are substituting. So the lambda 2 places, 6 we substituted. X also the dominating in 2 places. So the 4 we substituted. And e power minus 6 is there, that it is written 1 by e power 6. That's what here. So now we know it. That simplification we got it. 6 power 4 by 4 factorial, it's nothing but 54. We can use a calculator and we can find what is the value of e power 6. The final answer is 0.1339. This is the probability when x equal to 4. Here just to understanding purpose it has kept. There is average is 6. Just we are writing. Average is 6 means compulsory the 6 number will be there. So up to infinity it goes on. That is the reason here in the question, if you are noticing, use Poisson distribution formula, that it is not at all given, but we are using Poisson. So it's not only one distribution we are learning, more distributions are there. Binomial distribution is there, Poisson distribution is there, normal distribution is there. So in these, among these many distribution, this particular problem, why we have to select Poisson distribution? The reason is, the main is average. The mean, if it is given, first preference giving 2 words, we can go to Poisson distribution. So the Poisson formula, lambda is given and x is a specific target. To satisfy the formula, all the data are which is available, we are able to pick from the question. Problem. So now the average number of phone calls or per minute coming into a switchboard between 2 p.m. and 4 p.m. is 2.5. That is particular time we are taking. That is the phone calls which is coming from 2 p.m. to 2 to 4. Here again the word, the starting only average it is there. So we decided better we can go this problem to solve. We can take help from Poisson distribution formula. So here 2.5 it is there. So the lambda easily be picked. Determine the probability that during one particular minute there will be 4 or few, that is less than 4. More than 6 calls, so greater than 6. Now Poisson distribution formula is there. We'll concentrate the solution. That is, this is a specific target. That is x, it's nothing but the phone calls per minute coming to the particular time. The first question is, this is the lambda, given lambda equal to 2.5. Because of this average, that is the mean of the Poisson distribution, it's nothing but lambda. So the Poisson distribution formula which is written here, e power minus lambda into lambda power x by x factorial. Lambda, we know it, 2.5. X is our specific target. The first equation is 4 or fewer. So that less than or equal to 4. So now the Poisson, x is less than or equal to 4. 4 is included. That's what we wrote it, up to 4. Less than 4. So it takes the value, we know it, the Poisson, the distribution formula. Here, x is taking the value from 0, 1 onwards up to infinity. So our question is less than or equal to 4. Equal sign it is there. That is the reason we stopped up to 4. First, we are applying x equal to 0. That is in the formula. In the formula, here we are noticing x place we are putting 0. Yeah, 2 places we substituted. But lambda also we know it. That is a 2.5. So to calculation purpose, to save the time, at present, right now we are not substituting. Only we are targeting, this is x equal to 0. Here x equal to 1, we can notice it. Here 1 factorial. For this is the Poisson formula. Here if you are noticing, x is taking the value 2 factorial. Here x is taking the value 3 factorial. Here we are noticing x is taking the value 4 factorial. Now here lambda power 0 is there. So a power 0, the value is 1. Down is 0 factorial. That is 1 divided by 1 equal to 1. So only e power minus lambda it is written here. Next, e power minus lambda, lambda power 1. This all we didn't touch. Just they are written as it is. Only the changes we brought in the first term. That is, this lambda power 0, it is replaced by 1 according to exponential law. 0 factorial, it is replaced by 1. Now, we are noticing in this complete, all the terms, e power minus lambda, it is there. Better we are taking outside. So here, e power minus lambda, it has come completely out. So the balance is 1. Here, lambda power 1 by 1 factorial. Here, lambda square by 2 factorial. Lambda cube by 3 factorial. Lambda power 4 by 4 factorial. So, initially here only one doubt we got it. Lambda we know it, the value is 2.5. Why we didn't substitute in the initial stage itself? If we are substituting also, nothing wrong in it. Better compulsory, so many terms are there. So nearly 1, 2, 3, 4, 5. 5 times we applied the binomial distribution formula. That e power minus lambda, it's a common term for every. So we are getting an idea that better we can take e power minus lambda as common term to consume the time only. Now the final stage we substituted. If you want to substitute in the first earlier stage itself, nothing wrong in it. We can adopt that procedure also. Now 1, here we substituted wherever lambda, we substituted the lambda value is 2.5. Here also 2.5 the whole square, 2.5 the whole cube, here 2.5 the whole power 4. the factorial and all as it is written. Now, so this is e power minus 2.5. Here 1 is written. This is 2.5. Here simplification we got it 3.125. Here 2.6042. Here 1.6276. The final answer we got it 0.8911 is the result 4 or fewer, that is the probability of. So just here, just some indication it has kept on what point we will be taking the Poisson distribution. That is, it tends to infinity. Then Poisson distribution formula we will apply. So you can see it here. It is it is Poisson. If it is there in the question, it will be dominated by average or mean. If it is there towards Poisson, we will be moving. And the total number, it won't be given at all for the Poisson distribution formula. Only it will be given average. That is the reason here also, just understanding purpose, to increase our understanding level more, 0, 1, 2, 3, 4, so on it goes on. 4 or fewer. The next question is more than 6 calls. Yeah. So here more than 6 calls. So 0, 1, 2, 3, 4, 5, 6, so on. Because it's a Poisson. We don't know. The question it is not at all given. Total how many calls it has come. It is not at all given in the question. If it is given total 1000 calls, then we will write 6, 7, 8, 9 up to 1000 we will write. Nothing is given. Simply it is given average phone calls are coming during that particular time 2 to 4. That is the reason just we kept it 6 ... so on. Fine. Now more than 6 calls is our question. It is greater than 6. Here 6 is there. 6 is not included. If it is equal sign is there, we will include. So our required data is, here we can see the beauty of this sum. The what is that? The Denis Poisson, the French mathematician. So it goes on, you can, the greater than 6 is there. 6, 7, 8, 9, 10, it goes on. Because we don't know what is the total number of phone calls coming to the particular time. It is given only average and it goes on. So, but this goes on, this data only is required for this answer. This question, this is the data only it is required. But here we don't know what is that last one. It is infinity. Then we will do the smart work. This is the data we want it. This is the only required, needed information to solve this question. But it tends to infinity. Fine. Smart work, what we can do it? We know it, the total probability is 1. Minus, this data is unwanted data. It is not at all related, these data to this question. So which is not at all related, the data from our total probability is 1. So 1 minus this we are subtracting. Then the required data will be coming out. That concept we are using here. So fine. Here 1 minus p of x less than or equal to 6. Here 1 is written, here minus is there. So x is less than or equal to 6. 6 is included because of this equal sign. Less than 6. So 0, 1, 2, 3, 4, 5. So 1 it is written, minus is written. Now, Poisson. This is the Poisson distribution formula. That is, here x is there. The x place what we will substitute? 0 we will substitute. For this x place we will substitute 1. For this we will substitute x place 2. Here x place 3. Here x place 4. Here 5. Here 6. E power minus lambda we are not touching, keeping in our mind compulsory every term e power minus lambda is there, better we will take as common out. The final stage, the lambda we will substitute. We decided. So now, 1 is minus. The first term only there is a change. That is here only. Remaining and all as it is written. That is, what is the change we brought in here? That is lambda power 0, that is the value a power 0, it is equal to 1 divided by 0 factorial, that is 1 divided by 1. Now 1 is there, minus is there, here is there. We have taken e power minus lambda as common out. Here the balance is 1, here lambda by 1 factorial, lambda square by 2 factorial, lambda cube by 3 factorial. Lambda power 4 by 4 factorial. Here lambda power 5 by 5 factorial. The last one is lambda power 6 by 6 factorial. So now we substituted in the place of lambda everywhere 2.5. So we know it is just they have kept it mean of the Poisson distribution is lambda. So now, if you are noticing here, so here 1 is there, here 2, here 1 should come, 2.5, this values everything. We are getting the first one as 1. So here also 1 is there. So the 1 minus e power minus 2.5. So all the simplification which is done. The final result, if you are noticing, using the calculator, we can find this e power minus 2.5. The final result we got it 0.0142. This one is nothing but this one. That only here written, here. So one more problem we can do it. Average number of accidents on any day on a national highway is 1.8. Average, fine. We fixed our mind, better we can go towards Poisson formula. Lambda equal to 1.8. Determine the probability that the number of accidents are at least 1, at most 1. So the mean of the Poisson distribution is lambda. This is the Poisson formula, that is probability of x. It's nothing but e power minus lambda into lambda power x by x factorial. The solution of this particular problem is mean of the Poisson distribution is lambda. The question which is given, the average which is 1.8. That is the reason here we have taken lambda equal to 1.8. So the Poisson distribution formula is P of x equal to x. So P of x equal to e power minus lambda into lambda power x by x factorial. The first question is at least 1. At least 1 mathematically the inequality is greater than or equal to, just it is a Poisson. So 1 is there, so it will 0, 1, so on. We don't know where it ends because it is infinity. Now greater than or equal to 1 is there. This is only our question. At least 1 means greater than or equal to. 1 is there, so we are going to greater than or equal to 1. So 1 Next 2, 3 is there. But where is the ending? We want it, the data equal is there. So 1 is included. This is included, this is included, this is included, up to ending what is there? Infinity. This is the required data for our question. This is very, very clear. But if we know the ending, it is easy for us. But not at all. It is infinity. That is the reason we selected the first Poisson formula. If we know the ending, we will go to binomial distribution formula. There is a difference between binomial distribution and Poisson distribution. So we can see it here. So at least that is a greater than or equal to 1. Now here 1 is there. So this is completely which is included. This is unwanted the data. Same, we will do the smart work. So this is only probability of at least 1. It's nothing but P of X greater than or equal to 1. So now this is unwanted result we don't want at all. So the smart work 1 minus probability of X equal to 0. Probability of X equal to 0. So total probability we can subtract from that unwanted. What is the data we want, it will come out. That is a smart work we are doing. It is must for Poisson we have to do it. Then only we can reach the solution. So 1 it is written, minus it is written. Here we are going to apply the Poisson formula. In the Poisson formula, lambda as it is written. Finally, we will substitute. Already lambda which is given in the question, that is 1.8. That is also one of the reason in the question average is given. Immediately our mind decided what we can apply Poisson distribution. Then regarding Poisson distribution, what we selected, it is correct or not. So many calculations we did in our mind. Finally, we decided, yeah, towards Poisson distribution we can move. So now X equal to 0, 0 we substituted. So we know it. Here this is lambda power 0, the value is 1. 0 factorial, the value is 1. So here 1 minus e power minus lambda. So the lambda is nothing but minus 1.8. Here we can see it here. So the final answer we got it 0.8347. Now utmost 1. So the utmost 1 mathematically it is less than or equal to. Now we can see it. This is the Poisson formula. Utmost 1 is a probability of utmost 1. Mathematically we know it. It is X is less than or equal to 1. 1 is included because of this equal sign. Yeah, better. So less than 1. Less than 1, which data which is available? 0. So these two data only required. Fine. So P of X equal to 0, 1 time Poisson formula. When X equal to 1, 1 more time Poisson formula. So we applied. Here we can see it. X 2 places it is there in the Poisson formula. That is here and here. So X is equal to 0. That is our specific target. Here X equal to 1. In both e power minus lambda. No. Here we applied the values. That is here a power 0. That is lambda power 0. It's nothing but 1. 0 factorial. The value is 1. So e power minus lambda into 1 by 1. It's nothing but e power minus lambda. This e power minus lambda, e power minus lambda. Lambda power 1, it's nothing but lambda divided by 1 factorial. 1 factorial, it's nothing but 1. So here we are finding e power minus lambda is common. We have taken, here is remaining is 1, here the remaining is lambda. we are substituting the lambda value which is given in the question, that is lambda is nothing but 1.8, here also 1.8. So this we can multiply, the result we got it 0.4628. The next problem we can concentrate. If your Poisson distribution is such that P of x equal to 1 into 3 by 2, which is equal to P of x equal to 3. Find P of x greater than or equal to 1, P of x less than or equal to 3, P of x lies between 2 and 5. These three questions we are going to solve. First, so far we discussed the problems. They made our job very easy. That is, in the question itself, there is a word, it is given average. So lambda we have taken compulsory. The specific target will be, that is at x equal to 2 or less than 2, at most 2, or at least 2. Yeah. Then the specific target we applied, we have come out. So for what we discussed those problems. But here they gave some condition, that's it. There is no lambda, nothing is given. But the probability of x equal to 1 into 3 by 2 equal to, so when x equal to 1, x equal to 3, but this is multiplied by 3 by 2 times. Yeah, now, so this 3 by 2 we have taken as it is. The P of x equal to 1 is there. We know the Poisson formula, e power minus lambda into lambda power x by x factorial. So the x, the two places we substituted 1. Here also the same Poisson formula, x place we will put it 3. Yes, we substituted. Now 3 by 2 e power minus lambda, lambda power 1 by 1 factorial, which is equal to e power minus lambda into lambda cube by 3 factorial. So 3 by 2, here this e power minus lambda, here e power minus lambda, both are getting cancelled. So the remaining is lambda power 1 by 1 factorial. Here the right hand side is lambda cube by 3 factorial. So 3 by 2, lambda power 1, lambda cube, 3 factorial, it is written, we know it. 3 factorial is 3 into 2 into 1. It's nothing but 6. So here the lambda cube by 6, this one minus 3 lambda by 2 equal to 0. We are taking actually. So lambda cube LCM we have taken. Lambda cube minus 9 lambda by 6 equal to 0. So lambda cube minus 9 lambda equal to 0. We got a cubic polynomial in terms of lambda. So in this both lambda is common, we have taken out. So the lambda is written. This is nothing but a square minus b square formula, a plus b into a minus b. So here a plus b, here a minus b. Our b is playing the role 3. That is in the place of b square, 9 is there. It's nothing but 3 square. Compulsory we should get lambda, 3 values we have to get, because ours is what? Cubic. In terms of the lambda we got it in terms of cubic. So this is only our question. So this is the last step in the previous slide. So lambda equal to, so this lambda equal to 0. From here lambda plus 3, it's nothing but lambda equal to minus 3. So lambda minus 3 equal to 0, which is nothing but lambda equal to 3. 3 values we got it. That is for lambda 0, minus 3 and 3. But we are going to take only this 3. The reason is the starting itself, the definition of Poisson, which is given very clearly, e power minus lambda into lambda power x by x factorial, where lambda is the parameter which is greater than 0. According to that condition, 0 and minus 3 are neglected. We are taking into consideration only plus 3. So the Poisson distribution formula is e power minus lambda into lambda power x by x factorial. Our lambda value, just now we got it, 3. So this is the question which is asked to us, that is x is greater than or equal to 1. And the second question is x is less than or equal to 3. The third question is x lies between 2 and 5. So we are noticing the big number is 5. So understanding purpose, this step which is written here completely to avoid the careless mistake and understanding level to increase, only this step it is included in the rough column which is kept. Yeah. The first question is greater than or equal to 1. Yeah. 1 is included because of this equal sign. Yeah, 1. Yeah, just a minute. Yeah, 1 is included. Fine. Greater than 1. 2, 3, 4, 5. Goes on up to infinity. So this complete data, it is required, it is must, it is needed for our question to solve, to reach the destination of solution. So it is a big task. How many times we will apply the Poisson distribution formula? It is meaningless. So better the smart way. It is not smart way. It is must and it is required here. That is the unwanted, the data is this one. So the total probability, we know it 1. We will subtract from the total probability this unwanted, the data 0. Yeah, we did 1 minus p of x equal to 0. So 1 minus this p of x equal to 0. It's nothing but, so the Poisson, the distribution formula is nothing but e power minus lambda into lambda power x by x factorial. Our x, in the place of x, 0 it is there. So x dominating in 2 places, they are replaced with our specific target 0. So e power lambda power 0, the value is 1. 0 factorial, the value is 1. So 1 minus e power minus lambda, that's what it is written here. Lambda, we derived it, we solved now and we got it lambda 3. So it is written here. 1 is written as it is, minus is written as it is. E power minus 3 value is 0.04979. So calculated, the value we got it 0.95021. Now, the second question we are going to target, that is probability of x is less than or equal to 3. So equal sign is there. 3 is included. Less than 3. See the data. 0, 1 and 2. So this is only our required data. 4 times we are going to apply Poisson distribution formula for x equal to 0, x equal to 1, x equal to 2, x equal to 3. Yes, x equal to 0, x equal to 1, x equal to 2, x equal to 3. The Poisson formula, e power minus lambda, lambda power x by x factorial. So in the place of x, we put it 0 for this. Here x place we put it 1. Here x place we put it 2. Here x place we put it 3. Everything the second, third and fourth, the terms are written. That is here 3 factorial we put it 6. 2 factorial we put it 2. 1 factorial is 1, that's what it is not written. 0 factorial is 1. Lambda power 0, a power 0, 1. So we simplified. The particular factorial, the value is also written. Now we are noticing all the 4 terms, e power minus lambda, it is there. We have taken out. So here the balance is 1. Here lambda square by 2. Here lambda cube by 6. So e power minus lambda of 1 plus lambda square by 2 plus lambda cube by 6. So the lambda which plays the role, in the place of lambda we placed it, the value 3. So here lambda square, our lambda is 3. So 3 square 9, here 3 cube 27. So e power minus 3, here completely we have taken the LCM. 6 is playing the role of LCM. Here 1 into 6, here 3 into 6, here 2 is there. So 9 3s are 27. Here 27 as it is. So e power minus 3, this calculation is done. We got it 78 by 6. So e power minus 3 into 13 into this e power minus 3, the value is 0.04979. So the final result is 0.64727. So this question also we solved it. The final one is x lies between 2 and 5. So we are noticing here equal sign is there. Because of that equal sign, this 2 and 5, they are also included. So 2 is included, 5 is included. So x lies between. This is mathematical notation. How we will read? What is the meaning of it? X lies between 2 and 5. 2 and 5, they are included because of this equal sign. Now these 3 and 4 also included. So that is the reason here 2, here 5, 3 and 4 in between also included. For x equal to 2, 1 time Poisson. So noticing x is dominated by 2. Here the Poisson x is dominated by 3. Here in the Poisson x is dominated by 4. Here in the Poisson x is dominated by 5. Now here e power minus lambda square 2 factorial, it's nothing but 2. The numerator is written as it is. 3 factorial, it's nothing but 6. Here the numerator as it is. 4 factorial, it's nothing but 24. The last term, the numerator is as it is. The denominator is 5 factorial, it's nothing but 120. Now everywhere, all the 4 terms, e power minus lambda is common. So we kept it outside. The remaining lambda square by 2, from the first term. From the second term, lambda cube by 6. From the third term, lambda power 4 by 24. And the last term, lambda power 5 by 120. So this is the last step. So now we are noticing in the numerator the first lambda square, lambda cube, lambda power 4 and lambda power 5. So the least one is lambda square. We can take it as common. So it is kept out. So here the remaining is, the first one is 1 by 2. From the lambda cube, lambda square has come out. So lambda, the third term, lambda power 4, it is reduced to lambda square. The last one, the lambda power 5, it is reduced to lambda cube. So now we substituted the lambda, the value is 3. So 3 square, it's nothing but 9 e power minus 3. Here also the lambda place we put it to 3. Here lambda square, it's 3 square, 9. Here lambda cube, it's nothing but 27. So 9 into e power minus 3, this 120, it has taken LCM and we got it. So 1 is multiplied, here 2 is there. So 1 is multiplied by 60. Here 3 is there. 120 is there. So 3 into 20, 60. Here 9 is there. Here 9 into 5 times 45. Here 27 is there. So this calculated one, we are getting 192 by 120. So the simplification in decimal, it is given 1.6. So 9 into this e power minus 3, the value is 0.04979 into this 1.6. The final, the calculated, the value is 0.716976. So the completely we have taken understanding purpose to avoid the careless mistakes. This is the steps we put it in the rough, which help us to go in a correct direction. Yeah, we have come to a conclusion of this lecture video, that problems on Poisson distribution. Initially, we have taken Poisson distribution. We defined what is the Poisson distribution formula. That is e power minus lambda into lambda power x by x factorial. X is taking the value from 0, 1, 2, 3 up to infinity. It goes the formula which is given by Denis Poisson, the French mathematician. That is, he did binomial distribution formula. The limiting case of binomial distribution, it's nothing but Poisson. The mean and variance of the Poisson, that is lambda. And the Poisson distribution formula, we applied this formula in different types of problems. This we have taken as, at most, if it is given the inequality mathematically less than or equal to, exactly equal, at least greater than or equal to, and this concept we focused it. From this concept, we are able to understand what is the difference between binomial distribution and Poisson distribution. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.